Okay, time to get started. We have an assignment due today. I'll be working on getting up the last assignment of the quarter. And as we finish first follow and LL, we can get up the last project of the quarter as well. My recommendation with this last assignment is to get started with it and get it done as quickly as possible, because there will be a little bit of a crunch at the end of the quarter for as I assign this project and make it due. You don't want to have a homework overlapping that. It's going to be a bit of a pain. Really want to get a hold of me. Don't they know I'm teaching? I'm going to get a random call saying, is it an emergency? No. All right then. All right, so last time we were talking about the first function, and we had a bit of example with the first function. As a reminder, this is just, you calculate it for any, I guess, sequence of terminals and non-terminals. And if it starts with a terminal, then the first function is just that terminal. If it's a non-terminal, then it's the first terminal that any production sequence starting from there could produce. So if it's first of S, then we look for every right-hand side production, S arrow something, and take off the first terminal of each of those productions. And if that goes to a non-terminal, then we have to expand it into however many ways that can go until you derive some terminals. But we found that we had the hint at the end that lambda could make this a little bit more complicated, because if a non-terminal can go to lambda, then we have to consider what comes next after that. So let's get some experience with that. Anyone have any questions before we move on to an example first function with lambda in it? All right, here's a grammar. Calculate the first of each non-terminal. So we want to first of S, first of A, first of B. Where should we start? Which one of these is easiest? First of S, A, or B?
Yeah, the easiest is gonna be B, obviously.
Yeah, B's not so bad. You
Or
add
A,
B,
sorry.
either both A and B
Yeah.
aren't too bad. A goes directly to C and D without any non-terminals, so first of A will just be C and D. For B, we actually want to add lambda to the first of B, and the reason we want to do this is if we ever come back to it and say, what is the first of B? We want to see that lambda and say, we want the ability to move past it in whatever calls it. So we're going to define first of B as B and lambda. This lambda does not get printed if we ever try to say what can be produced by B as a terminal. We would print just the B, but that lambda tells us when we go through first of S and see the non-terminal B at the beginning of one of those right-hand sides, then we look at first of B, see the lambda, and that tells us that we should also look at the character after the B, because it is possible that B goes to lambda. So first of S is going to be defined at the beginning as just the first of every possible right-hand side. So this gives us A, and it gives us the first of capital B, capital A, D. And this is why we need to store more than just that first character. Because if we just said first of capital B, then we wouldn't be able to refer to the character after the B. So always store the entire right-hand sides programmatically when you do this. Again, when you're doing this in your head, it's not exactly the same problem, but programmatically, you need to store that whole right-hand side. B can go to lambda, so we have to add first of A, first of capital A, to this as well. So calculating first of bad, we see first of B is B and lambda. We add B to first of bad, but since B can derive lambda, we have to consider first of the next character as well. The next character is the non-terminal A. We've already calculated that as C and D, so we will union that. So first of bad is B, C, and D. So now we can redefine first of S as the empty set, which is first of S, union A, which is the first of A, capital S, C, union the first of bad, which was A, B, C, and, or sorry, B, C, and D, which gives us the set of everything, A, B, C, and D, as our first of S. Questions about that or how that works? That's straightforward. Do we see how there is some sequence of production starting at S that could generate every character A, B, C, and D as the first terminal in some derivation starting from there? To get A, we go straight from S to the production that starts with lowercase a. To get lowercase b, we're going to pick right-hand side, and then this B left-hand side that produces the B first. To get C, right-hand side, this B goes to lambda, this A goes to C, and to get D, this B goes to lambda, this A goes to D, and now we have some path through the grammar that produces each of those as the first terminal. And that's exactly what I go into in the next slide. Working from the opposite direction to intuitively show that it's correct. It's really a two-step process, of which this is going to describe one of them, but it's a good intuitive step to take on an exam or on a homework problem to ensure that your answer is complete. If you have an answer for first of S, you want to be able to show some derivation such that that terminal begins the string starting from that non-terminal. So if we were doing first of S, we can have derivations that show some string that starts with each one of those terminals. Do note though that this is only half of the problem. Because we also have to show that it's complete, that there's no way to derive anything else. So how does first of A, how do we know it doesn't have A or B embedded in? And that's a little bit harder to do. You'd have to iterate over every possibility going through the grammar, so it's much better to just really, I think, this is the fast, easy thing you can do to at least ensure that everything that you have added is in there. Questions on first? Do we feel like first is intuitive at this point?
A bit less. Screen as well.
Yeah. Yeah, make sure this is intuitive because it will also be used in follow. This will be a subroutine within follow. Maybe a show of thumbs from people. How do we feel about first? Okay. Seems fairly reasonable for where we are. Some homework will certainly help with practice. But the harder of these two is follow. So the goal of follow, kind of like how first says, given a particular left-hand side, what are all of the terminals that can be the first element from a derivation starting with that. Follow says, what are the sets of terminals that can immediately follow some derivation of this? So if we were looking at follow of capital A, we're going to look at everywhere on a right-hand side where A appears and say, what could be the first terminal derived after some expansion of that? So defined for a non-terminal takes as input a non-terminal and outputs the set of terminals that can appear immediately after that non-terminal in some production's right-hand side. And the reason we care about it is we need to be able to choose which production to expand based on what could follow it. So we see in a look ahead on the string, we need to derive some kind of A, and we need to figure out, all right, well, what could we expand such that that A comes first? What can we do such that that A comes after some expansion? To do this, we need an additional symbol, the $sign, what we're going to use to indicate that what could follow is the end of the string. So this is by definition used in the follow of the S production, because S can always represent the entire string. So what could follow whatever we do with S is the end of the string, by definition. But they can also appear in other follows, saying that after we expand this non-terminal, what we could have is the end of the string. So first step, add $, to follow of S. And then once again, as you're going to be implementing this as part of LL parsing, I have some pseudocode for you to look back on. So step 1 says add $, to follow of S. And remember that here V and W can be any terminal or non-terminal, even though they are written as lowercase. For every left-hand side arrow, some character followed by some other non-terminal B, then whatever is in follow of A is in follow of B. Does it make sense why that is? Whatever could come after A somewhere, like let's say somehow we get capital A, lowercase a in some derivation. This capital A can become something that ends with capital B when we expand this. So there's going to be a capital B here. And so anything that could follow A could also follow B if we just use this particular production that turns the A into something that ends with a B. So whatever this set happens to be, it's all, every element of this set is also in this set. So that's what this is saying. For every where we have a non-terminal in between some terminals or non-terminals, then if we have to now look at first of W and figure out taking out lambda, because that doesn't matter, whatever is in first of W is in follow of B, which makes sense. So if we have something followed by BA in a derivation, then whatever is in first of A has to be in follow of B by definition. So we will be using first as a subroutine of follow whenever we have back-to-back non-terminals. Which of course is very frequent. Does that intuitively make sense? After some expansion of this B, whatever follows that is, or could be, whatever is in first of A. If there's lambda in that W, then whatever could follow A is also in follow of B. Because if that can go to lambda, then we have a recursive definition of follow. Because it can go away, so whatever follows the A can also follow B. We'll see this play out with some examples, I think. But this is the entirety of follow. It just is a little bit harder to visualize or to see intuitively, I find. Let's give you an example. Our old friend, our first grammar from first. We're going to do this for the same sets of grammars that we did for first, but follow for each non-terminal in this grammar. This is not first, this is now follow. What could be the first non-terminal that comes after an expansion of each of these non-terminals? So I find S is easier than A, so let's calculate follow of S first. What was that first step? What do we know is in follow of S? Dollar. We know that dollar has to be via some way, with the way we start one of these derivations is we say S arrow something, and there's some derivation to this. What is immediately following this S? It's the end of the string, so there's nothing there. The way that we're going to define that is we've reached the end of the string is with that dollar sign. By definition, our start non-terminal must be followed, at least potentially, by the end of string. What else could follow S? Yeah. Here on the right-hand side, we expand S to be whatever it does, and whatever follows that is potentially B. So take a second and convince yourself of this. Draw out some expansions using this grammar and try to come up with the set of terminals that follows some S wherever it happens to be. So S becomes A becomes C. This S expanded to be A, expanded to be C, and now what follows this S, kind of as a what happened after that, is just empty from some expansion of that. On the other hand, we could make B follow it if, I'm just going to start drawing these vertically, S goes to A, S, B, and then S goes to A, and this goes to B, A, and this goes to C. What followed this S? This entire expansion is the definition of S, so what followed it? The B. Nothing else inside of this matters. Is there any way to get any other terminal following some expansion of S somewhere in this grammar? Convince yourself the answer is no, because it is. There is no other way to get any other terminal following that S. It's either the end of string marker or it is a B. So that is your follow of S, that's set. B dollar. How about follow of A? Take a second and work out every terminal that can follow some expansion of A in this grammar. B or A? How can we get, let's start with an A. How could we get an A following an A? So we start with S, what does S become? I think that has to become ASB. Not necessarily, could go directly to the A. Yeah, let's do it straight to the A. S goes to A goes to B, A, and now after this A is defined, whatever that happens to do, doesn't matter if that becomes another BAA or a C, after that we have an A. So this shows us that A is in follow of A. What else? We said B. How do we get B?
BA, yes, ASB, and then
S goes to ASB, this S goes to A, and then however this expands, it doesn't matter what follows that A, is that B? Is there anything else in follow of A? Convince yourself the answer is yes, because there's one more thing in follow of A.
string.
Yes, dollar. Right here, what comes after this A? The end of string. If you're doing a depth first search, we've already defined everything. By the time we return to A, there's nothing else that can come after that, so it has to be the end of string mark. So yeah, follow of A has three components, A, B, and dollar. Questions on this follow example? This is the programmatic way of approaching follow. And I have historically found that if I draw it out and explain it intuitively, it catches on better than if I explain it programmatically. So I try to explain it, how you might visualize it and see it working out as a problem, and then here is how you would calculate it programmatically. Any questions? Ready for the next example? All right, here's another grammar. It's the bad grammar. Yeah, same grammar, but now let's calculate follow of every non-terminal. Follow of S, A, and B. It's especially challenging because of that lambda.
What comes to be, yeah, the non-terminal or main terminals to the right hand side, non-terminal.
All terminals to the right-hand side of that non-terminal on the right-hand sides. And then if there are back-to-back non-terminals, then you have to query first. And then everything from first to the second non-terminal. To follow up the first non-terminal. But if that second non-terminal can go to lambda, which first would identify. So it's reasonably complicated. A little more complicated than first. A good question to ask is, which one of these is easiest to answer? Is follow of S, follow of A, or follow of B easiest?
I think follow with S.
Be right. That's a good way for me to determine how intuitive this is to people is. So follow of S is going to contain two elements. What are they?
C and the dollar sign?
C and dollar, and that is it. The way that I'm going to have people do this is, so you're going to add dollar to follow of S, just by definition. But following that, you're going to look for every case of it appearing on a right-hand side and say, what follows that? Yeah.
Well, actually, so I have a question. Why is D not also in that follow?
In follow of S?
Yes.
How would you create that? So we're going to start with S, and then we're going to make some kind of derivation from here. And what follows either this S or some S internally is going to have to be a D. How would we do that?
The first one A, and then follow that to D.
A, S, C, and this S goes directly to D.
No, the A.
A goes to. So here we have an S where after we expand this to be whatever it is, what follows it is a C. And here, when we depth first search this and return to this S, what follows it is dollar. So you're thinking of follow as the second non-terminal maybe, as opposed to what follows the full expansion of it. Because then you could have the first, the second. So it isn't what follows the first, it is what follows the entire expansion of.
Okay,
So here we have kind of a triangle that's going to be the expansion of S, and the next character after that is that C. Then here is a much larger version of that triangle being the expansion of this S, and what follows that is the end of string mark. So yeah, that's our definition of follow, but that's an excellent point to make because I can see how that would make a very big difference in what you add to your follow. So yes, follow of S is C and dollar. Which one of these is next easiest? A is probably the most challenging. But let's go through it. So where are all of the A's on the right-hand side? We have 3 of them, here, here, and here. So we're going to need to query for each one of these, what could follow each one of these? Some of these are easy. This one is very easy. What can follow this A is this D. So since it's a terminal, we're done. We just know that D is in follow of A. This could be the end. So what follows A could follow A. That doesn't really help us very much. It's self-reference. So that's not going to add anything new to follow of A. But we do know that when we see, so that doesn't do anything. When we try to follow A, we now have to add what is in first of S to follow of A. We already calculated that, but if we hadn't already calculated that, we would now have to see that S can become A as its first, S can go to B, which can add B, but it also can go to lambda, which means we have to look at first of A, which is C and D. So what can follow A from this A is all of A, B, C, and D. We get a duplicate D from here, but they're all contained within first of S, which can follow A. So that's the intuitive way to think about it. Does it make sense how we could get that? Maybe it's worth drawing out and seeing that what can follow A in some capacity could be any of A, B, C, or D. All right, so we'll start with A. We don't need to derive going from S to A. We can just start with our query non-terminal. How can, from here, I guess we probably do want to start from S, just to see it happen. Let's start from S. How can we expand to be able to see what follows an expansion of A is an A? We pick the left-hand side or the right-hand side of our expansion of S. So it has to be the left-hand side. So we're going to get A, S, C. All right, so what follows this A has to be an A. How do we get there? Does this S become a left-hand side or a right-hand side? Yeah, has to be the left-hand side. So this becomes A, S, C, and then we kind of draw our triangle in here. It doesn't really matter what A expands into, but what follows it next in a depth first search. So we depth first search, and as we get back to this A, what follows it is this A in depth first search order. So that gets us an A. How do we get a B out of it? Yeah, so we need to, same thing, make our S the A, S, C, then this S is going to become B, A, D, this B becomes B, D, D, and now we get our triangle of expansion here, and whatever follows this in depth first order, we return here, we go to the next, and we see that it's this B. So that's a B following an A. How do we get C out of it? This one's a little harder. Left-hand side or right-hand side? Has to be the left-hand side again. We'll get an option next time, which will be nice. A, S, C. This is gonna be the query A for which we follow and get the C. What do we do with the S? To make this as short as possible, left-hand side or right-hand side?
B, A, D.
Yeah, right-hand side,
Yeah.
gonna make this a lot easier.
And B goes to lambda.
B goes to lambda,
A
yep,
goes to D.
A goes to,
Oh, C, A.
yeah, this has to go to, this is really to C, A. And now we get our expansion of A, doesn't really matter what's in there, that is the worst triangle I've ever drawn. But what comes after that, when we return to this S, go to this S, go to this B, get nothing, go back, go down. This C is the next terminal that appears in depth first search order of this tree. So the C follows the A. And there's an easier, much easier way to see an A followed by a D, which is if we pick the right-hand side this time. And then the D immediately follows the A. Whatever this expansion happens to be, doesn't matter. The D is what comes immediately after. So that is one way to visualize how everything can follow the expansion of an A. Questions on any of those derivations?
So it's any set of non-terminals that can come immediately after, or any set of terminals that can come immediately after that non-terminal?
Yeah, after the expansion of that non-terminal.
So that's why when it's followed by a non-terminal, it's the first of it.
Yeah.
Non-terminal.
Yeah.
You can turn directly into that.
And if you've programmatically stored your lambdas, then the lambda does not become an issue in the follow. Because it only is an issue in the first. And if you've handled it correctly in the first, then parsing this should be easy. But if you have not handled that, or you're thinking about this intuitively, then you have to consider the lambda as part of your calculation of your first, when you're calculating your follow. But a precursor to calculating follow is always calculating first programmatically, because you're going to need to refer to it. So they're just going to need to be in lookup tables. So that was A. Any other questions on this? Really good work so far? All right, what's in follow of B? We need to identify everywhere it appears on our right-hand side. If it's immediately followed by a terminal, then that terminal gets added to follow. But if it's followed by a non-terminal, then we need to query what is the first of that non-terminal, which is going to be this C and this D. So we get C and D and D. The set of C and D is just C and D. And that is all that is in follow of B. So much easier than follow of A.
Special lambdas and follows.
Nothing that shows up by themselves. Because that lambda. Let me show. Here's everything we did for S and A. Intuitively, why don't we have to do anything with lambda and follow?
Because it's just not a character.
Yeah, so it's not a character, but if B goes directly to lambda, that doesn't really change, that's part of its expansion.
Yeah.
And when I drew that triangle, that it didn't matter what was in that triangle, or if that B can go away, the fact that B was there, it has to appear in some other capacity in a right-hand side, which is what we care about. Questions on follow? Show of thumbs, how much sense does follow make? About where we were with first, I'll take that. Similarly to what we did for first, we can verify that our follow function is correct, going through the logic that I've mostly drawn this out with on the board. So for each terminal in follow, we'll just draw out some tree and then think about a depth first search traversal of that tree. Note that it does not have to be a binary tree, it can be any, we did that with a tree with branching factor of up to 4 in the last grammar, but it doesn't really matter, you can still do. It's still a pre-order traversal. So very similarly, you can just draw it out and show that after some expansion, it immediately follows. Just don't expand the non-terminal that you are querying. So if we're looking for follow of A, just never expand the A and expand things that come after the A until you can produce a string that what immediately comes after from that is that character. Again, this doesn't show that it's complete, it just shows that it's correct. That everything that is in there should be in there, and not that there's something else out there that also should be in there. Any last minute questions or thoughts on first and follow before we dive into using them for something interesting? It will now be expected that this is intuitive. All right. Go grab the next one. We're into the last 2 slide decks of the quarter. These take a little bit of time to get through though. Both LL and LR are a little on the longer side. So we now can calculate first and follow, which just by themselves right now kind of seem like annoying subroutines to know, and let's see how they're actually used. So we can apply them by our old friend converting a context-free grammar to a non-deterministic push-down automata. So we're going to do that, and what first and follow are going to help us do as we do this is it's going to allow us to remove the non-determinism from the NPDA. To turn this into any NPDA based on a grammar can now be parsed as if it is a DP. Which is wildly cool. It's way cooler than it seems from the work that we have done. But this means that we can write an algorithm that can parse what would be otherwise an NPDA with intelligent lookups. So this will be how the LL parsing algorithm works. So let's start with our old friend, a CFG to an NPDA. We did this, yeah.
This is LL parsing.
Yeah. We did this with a grammar in Greibach normal form, and we found that that was very easy when we did it, but there will be no such restriction on us here. We're gonna start with an NPDA with 3 states. We have an initial state, and the entire purpose of that initial state is just to push S onto the stack. That's it. We know that we start with that start non-terminal, and via some expansion of that start non-terminal, if we can expand it into the query string, then we accept. If we can't, then we reject. Q1 is the state where all of the parsing happens. Every single parsing rule that we could possibly have happen will happen in Q1, and then Q2 is a final state. So that is the entirety of the NPDA that we are trying to construct. So transition from Q0 to Q1, all it does pushes us onto the stack. But then Q1 is going to be where all the fun happens. We need an element of every production rule, replacing the left-hand side with the right-hand side. So for every production rule where we have a non-terminal arrow, some set of terminals and non-terminals, we're going to add a transition that pushes on that sequence of characters. We then need to match symbols in the input in the order they appear on the stack. So we're always asking, is what's on top of the stack the next character in the input string? If it is, then we can match it and get rid of them. If not, then what should be on top of the stack is some kind of non-terminal, which is where the non-determinism was built in originally. We didn't know which way to expand that non-terminal, but we now have an intelligent way of figuring that out. So for every terminal, we're going to call this the ability to move past it. So let's give you an example of what this would look like. I'll leave this here for people to take a couple of notes. So this should seem just like an NPDA that we've constructed in the past. We just need rules for replacing left-hand sides with right-hand sides. And then rules for matching characters. If what's on the stack is the same character as what's in the input, then we can move past the character in the input and pop the character off the stack. But now we're actually putting the characters from the grammar. The grammar characters become the stack symbols. So we have both terminals and non-terminals being added to our stack in the NPDA. If we have lowercase letters, they'll represent terminals that we're attempting to map to the input string. And if they're non-terminals, then we need to expand them via some rule in the grammar. All right, so we'll start with something that is a little on the simpler side. Another of our favorite grammars. We've seen this a few times now. So given the rules on the prior slide, let's see if we can build an NPDA that mimics it. Mimics the LL parsing process on it. Fortunately, we're running out of time. So we'll probably have to come back to this tomorrow, but it's very exciting. So last minute announcements before we leave. We're getting a new assignment. Basically what we're through with Turing machines, everything that's going to appear on the next exam, that's going to be a week from Friday. So I'll get a study guide to you by this Friday so that we can do that. I have, as usual, moved a little bit faster than I have historically. I don't know if it's a good thing or a bad thing, but the exam won't have quite as much as we've covered so far. Kind of what's through the assignment that you're turning in this week, today. All right. I'll see you tomorrow, unless there are any questions. And we will go through this process on the start of class.